Good afternoon, everyone, and welcome to the next lecture of algorithms and data structures. In the last session, we completed the graphs chapter. We looked into graphs that have weights in their edges. We've also looked at two algorithms, shortest path and lowest cost, which are highly generic ones that we saw. There were lots of questions on these two algorithms today in the lab, which is good. That means you're starting to look into this also through the coursework, and it will take you some time to understand these two algorithms. Then we started with the complexity analysis chapter, and that's the one we will be completing today. Concretely, we wondered how long it takes to run an algorithm, and we saw that we can measure this, but if we do such measurements, it's not very reliable because we just have a limited number of inputs we can test depending on our computer and our operating system and many other factors. Measurements take longer or shorter. So this is not really useful to compare two algorithms. So instead, we're interested in a new approach, into a mathematical approach that allows us to describe the complexity of an algorithm for all possible inputs and not just a few. Concretely, we will count so-called primitive operations, and we saw those very simple operations, and we wonder how many of these primitive operations we need based on the input size n. So we describe a function that depends on n, and we will always focus or mainly focus on the worst case input and try to optimize for the worst case input. And typically algorithms that are optimized for the worst case input tend to perform well for most other inputs as well. We saw primitive operations and a couple of basis functions that we use to describe or that we use in our framework: the constant function, the logarithm function, linear function, quadratic function, the n log n function, and qubit functions, and other polynomials, as well as the exponential function. And we also saw how they develop. And when we build an algorithm, we actually want to pick one with a low complexity, so it scales better when the input size n gets bigger. We saw our core framework, and we looked at one example, the max function, and we wondered, what does the max function actually find max spend most of its time in when n is large, so the input size is large? And we saw it's actually that loop, and we saw then the O notation that allows us to describe the complexity of an algorithm. Importantly, the O notation is an upper boundary, so C times G of n must be greater than or equal to f of n. So f of n is limited or constrained by C times G of n for all n's starting a certain threshold. And that threshold is called n0. Before the threshold, that inequality may not hold true, but we anyway only care for large n and not initial n's that are small. We saw how we can have a term like 8n plus 5 and say this is O of n, the order of n, by finding the right n0 and c. And we saw how to interpret this, and that we will always say f of n is O of g of n. We don't really want to use this equal sign, because it's only something used for convenience, but it's not an equality. And we looked at a couple of terms and tried to simplify them or describe these terms in terms of the O notation, and a couple of best practices that are important to bear in mind. And then we started with our prefix averages. And the prefix averages is something we discussed quite in depth at the end of last lecture. And we had two candidate algorithms for implementing the prefix averages. The first candidate algorithm for computing the prefix averages takes O of n squared, because what takes long is what I have called here line 7, because I have a loop within a loop. And this statement here to compute the total in the inner loop will just be called O of n squared many times. We then try to eliminate the inner loop by replacing it with a sum. And sum is a basis function in Python, or a native function, and we can pass a slice of our input sequence S, but this still is in the order of n as a single operation. We run it n many times. So this algorithm is still O of n squared because we just replaced that loop with the sum function, but the sum function still internally needs some kind of loop. So maybe this runs a little bit faster on your computer because sum is implemented with a native function or natively, but it doesn't change the complexity. Now we will look at a third approach of how we can actually simplify the computation of the prefix averages. And remember, the prefix averages is we have a sequence S, and for the sequence, we want to compute a new sequence A, and we have in S the indexes 0 up to J. And J can be 0 up to n minus 1. And when we compute HA, this is the sum of SI, where the I starts with 0 and goes up to J. And we divide this by J plus 1. And we looked at plenty of examples last week of how this works. And we saw these two inefficient algorithms. And now we will look at a much simpler implementation that in fact avoids the inner loop, and we create a helper variable to wrong screen share in order not to recompute that sum from scratch every time. Rather, what we will do is something like this. We will implement our prefix averages 3 for our sequence. And the beginning is the same. We say, well, this is the length of S, and which is constant. Then we create our output list. And again, this is O of n because we need to create a list with n many zeros. And now we want our loop to go through, or to have J go through 0, 1, 2, 3, and so forth, up to n minus 1, because range goes up to n, where n is excluded. But this time, we are not building our total from scratch. Rather, the total is that sum. We will try to compute it in the first iteration of our loop. But then in the second iteration of the loop, we just add the next element on top, and we will not recompute the whole total from scratch. So we say this time we add something on top of total. And this is in fact the element Sj, which is just the last element in that sum. But that sum just starts with a single element. So this is the first one. And then in the second iteration, we just add on top the next element and so forth. So we just use one loop. And when the iteration of the loop finishes, we take this total and divide it by J plus 1 as before, and we return A. We have our prefix averages. We can call it on a sample like 3, 2, 9, and 10, for example, and it computes our prefix averages as we want, because you look at the first example, which is just a 3 that we put in. The next one is the sum of 3 and 2, which is 5 divided by 2. It's 2.5 and so forth. But we see that this actually just needs O of n much time, because we have the individual statements. We have the first statement, which takes constant time. Then this takes n much time, constant time. The return is just constant time. And then we have this loop, which runs n many times. But in the loop, we only have primitive operations. We have this index. We add something on total. Here we have a couple of primitive operations, like we have the total and divide it by a sum and assign it to an index in A, and then return A. But this only takes O of n. And if you put in a large sequence S, this algorithm will run substantially faster than the other two prefix averages, because the prefix averages 1 and 2 we implemented before, they take O of n squared much time. So imagine you put in like 1,000 elements, Then with your prefix average is 3, you need something in the order of 1,000 operations, not exactly 1,000 primitive operations, but something in that order, while you put in 1,000 elements in prefix averages 1 or 2, which is O of n squared, you need something in the order of 1,000,000 operations, which makes a huge difference. So now you've seen that complexity is actually extremely important. And we've seen one problem for which we have done 3 implementations, one of which is highly efficient compared to the other 2. What I just said about the prefix average is 3 and how to come to its O complexity is also described here in detail. But that's what I just said orally. Now, we will now look at a different notation. So far, we always dealt with the O notation, which is an upper boundary. So, so the amount of primitive operations is limited by some upper boundary. But now we want to have a lower boundary. And a lower boundary is just more or less the opposite of the upper boundary, while before we said f of n has its upper boundary, g of n. This time, c times g of n will be the lower boundary. So the definition looks very similar to what we had before, but we say we have our function f of n, the other function g of n. They are mappings as before. And this time we say f of n is omega of g of n. So a new sign, a big omega. We have still our constant c and our integer constant n0, which is greater than or equal 1. And this time we say f of n is greater than or equal to c times g of n. So we've just changed this inequality because with the O notation, we said f of n is less than or equal to c times g of n. This time f of n is greater than or equal to c times g of n for all n that are greater than or equal to n0. So it's more or less just the opposite of the O notation, while we said the O notation is an upper boundary, and this time the omega notation is a lower boundary. So it describes some lower boundary, meaning not a maximum of how much operations it takes at the most, rather how much functions it takes, how much operations it takes at least. So it's a lower boundary. And we will now have a couple of examples again to practice this, because now we want a lower boundary. And our first example is 5n to the 4 plus 3n cubed plus 2n squared plus 4n plus 1 is omega of 1, because we look at the lower order term, and that's the lower boundary. So it's omega of 1. I want you to do exactly or to look at the 5 next examples and find me their lower boundary, which is their omega. I will, in the meantime, while you look at that, I will copy and paste this to the iPad. And then once I have copy pasted that, I will switch the screen share to my iPad, and we'll compare your solutions. So the first one you will look at is 5n squared plus 3n log n plus 2n is omega of what? The next one, I'll quickly write them down, and you also think about how to solve them. So I've seen some solutions from your side, and we can compare them now. So the first, or example 2, is 5n squared plus 3n log n plus 2n is omega of what? I look at your solutions. It is n, because this is the lower order term. And again, we ignore constants and all of this, so this 2 just disappears. Then the next one is 20n cubed plus 10n log n is omega of n log n. Next one is 3 log n plus 2 to the n. It's omega of log n. So I'm always marking now the lower order terms. The next one is 2 to the n plus 2. As you remember, this plus 2 is also just a constant, because we can rewrite this as 2n times 2 to the n times 4, or 2 to the 2. Then the constant doesn't matter, so it's omega of 2 to the n. And the last one is 2n plus 100 log n. And here I got some disagreements from you in the chat. The lower order term is the 100 log n, so it's omega of log n. And one thing that is super important is, as we saw for the O notation, in the O notation we said we want reasonable upper boundaries. So if you just have a linear term, I don't want an exponential function as an upper boundary. It's mathematically true, but it really doesn't allow us to assess anything reasonably. Same here with the omega notation. Obviously, you could say for all these terms, it's omega of 1. So we could say it's omega of 1 because that's a lower boundary. It takes at least, obviously, constant time, but at least it actually takes more, like n log n, whatever. So again, pick reasonable lower bounds and not just the lowest bound possible. So it's exactly the same approach as for the O notation. There are some more examples if you look at the slides. There's some term like something like this. It's a 3n log n minus 2n. And in fact, this is an omega of n log n. Remember, this is a minus, not a plus. If you're curious about why this is omega of n log n, there is a justification here for you to look at that. But such terms we don't really need in algorithms and data structures, because we barely subtract time, rather we add time. So this is only for fun. But here I found a concrete C and N0 in case you're curious about how to solve this. But we don't need it. Then we will come to our next notation. So we now have an upper boundary, which is O. We have omega, which is a lower boundary. And we now can combine this into something that we call the big theta notation, or simply just theta. The same before, while it's called big omega, probably you just say omega. Like the big O, you just say O. And here we just say theta. Again, we have our function f of n and the other function g of n. And we say this time that f of n is theta of g of n if f of n is O of g of n and if f of n is omega of g of n. So g of n is this time both in the O as well as the omega. So g of n is both an upper and a lower boundary of f of n. It becomes a little bit more complex because we have this time two constants, c prime and c double prime. Both must be greater than 0. And we have our integer constant again and 0. And now our f of n, needs to be less than or equal to c double prime times g of n, because that's the upper boundary. But f of n must also be greater than or equal to c prime times g of n for all n's after that threshold, or as of this threshold. So this time, g of n is both a lower as well as an upper boundary. And this theta notation is actually super helpful because it allows us to say that two functions grow at the same rate. And we ignore, obviously, the constant factors. We have an example here, and I will show you this on the iPad to make this more clear. And once we have done this, we will compare the O and the theta notation and see which ones actually to pick when. So my example is, so the theta notation, we have a 3n log n plus 4n plus 5 log n. And we can say, we have this n log n, 4n, and 5 log n. We know its upper boundary, obviously. The upper boundary that is easy to find would be n log n. The lower boundary that would be easy to see is here log n. But in fact, we can apply the theta notation to this, and we can say that this is theta of n log n. And we can say this because we can work with our term. So our term from before, I'm just highlighting it in blue, then it would be more obvious. So 3n log n plus 4n plus 5 log n is greater than or equal to 3n log n. And this n log n is just this one. And the term that we have in blue, 3n log n plus 4n plus 5 log n, is obviously greater than or equal to the left one, because the left one is just a part of it, and we add something on top. But that term here in the middle is also less than or equal to 3 plus 4 plus 5 times n log n. And all of this holds true for n that is greater than or equal to 2. So this 3 comes from here, then a 4, then a 5, but it was a plus 4n. Now it's a plus 4n log n, and instead of a plus 5 log n, it's a plus 5n log n. So obviously, this right part here is greater than the middle part, and the middle part is greater than the left part, or well, greater than or equal to. So, and what we see is we have on the left this lower boundary, which is an n log n, and on the right, we have an upper boundary, which is n log n. So we can say this term from before in blue here, our 3n log n plus 4n plus 5 log n, is theta of n log n. And you're probably wondering, what is this theta useful for? And we can compare this to the O notation. I think most of the time you deal with algorithm complexity, you will be seeing the O notation. But I have another example for you. Say we have a function t of n, which describes the number of operations or primitive operations our algorithm needs. And it's something like 73 n cubed plus 22 n squared plus 58. And we can try to make a couple of statements on this term. We can say, first, t of n is O of n to the 100. This is obviously true because n to the 100 is a term that is greater than this greatest term here for a substantially or for a sufficient n0 and then all n's that are greater than or equal to our n0. Do you think that the first one is a good boundary? If you think what I wrote here, this O of n to the 100, if you think that's a good boundary, thumbs up. If you think it's a bad boundary, thumbs down. So I only see thumbs down. It's a very bad upper boundary. It's correct, but it doesn't provide really any insights. We can also say from a mathematical perspective that T of n grows asymptotically no faster than n to the 100 because it's an upper boundary. So asymptotically means for large n, it grows no faster than n to the 100. But we can make a better estimate and we can say T of n is O of n to the third. Because this is our largest term. So O of n to the third is actually a much better upper boundary. It's still true because T of n grows asymptotically no faster than n to the third. But we could also make a third statement and we could say that T of n is theta of n to the third. You can find the corresponding C's and n zeros to show this. And if you can show this, that T of n is theta of n to the third, then we can actually say that T of n grows asymptotically as fast as n to the third. So as fast as n to the third. And if we say as fast as, and before we said no faster than n to the third, it's also written in detail in the slides, then our last one here is obviously a much better statement and a much more precise statement than the O notation. So if you get a theta, it's a much better statement because it says as fast as, a much more accurate approximation, more or less exact actually, rather than an O, which is an upper boundary. The problem is for a lot of algorithms, finding the theta is actually much more difficult than the O. So throughout this course, probably in 95% of the cases, we would rather use an O or an omega. Probably 95% of the course will be using an O. In maybe 4% of the course, we'll be using a theta, and in 1% of the course, we'll be using an omega. So we'll largely focus on the upper boundaries because finding the theta of an algorithm is tricky. There will be one way how we can find it for a certain class of algorithms quite conveniently when it comes to recursion, but this is something we will see in a few weeks' time. What I discussed with you is also here in my slides, but we've just discussed this, so the slides, a lot of text for your revision if you wish. There are two more notations that I quickly want to discuss with you. One is called the small o notation. So we say this time f of n is small o of g of n. And this small o looks pretty much like the big O, but we have a less than sign. So f of n is less than c times g of n, while for the big O notation, it's a less than or equal to. This small o notation is, there's an example here. For example, we can say 2n squared is small o of n to the third. because it's a less than sign, but 2n squared is not o, small o of n squared, because this one here is not greater than this. And it's a greater sign or a less sign if you look from the left. And it doesn't include the equal sign. It's something you may see extremely rarely. We're not using the small o notation throughout this course. If you ever see it, you know what it is. And similar, like a small o, there is a small omega notation, which has the same effect. So it's a true lower boundary, and it's then a greater sign and not a greater than or equal to. But both the small o as well as the small omega are extremely uncommon notations. Then a few years ago, when I looked into more publications around quantum computing, I noticed that there is actually such a O tilde notation. So this is an O with a tilde on top. And I wondered what that was, because when I saw this the first time for a few years ago, I didn't know, maybe, yeah, 5 or 6 years ago, I just didn't know what this O tilde meant. And I looked it up. It's something that is becoming more popular now with quantum computing. And the O tilde notation is just a simplification. Imagine you have some term which is O of h of n times log n to the k. So you have h of n, which is a function, and you multiply it with various logarithm factors. And this may start to look extremely nasty, especially in the world of quantum computing, where you may have algorithms where there are a lot of these logs in the O. And maybe you just want to present it more neatly. And what you can use is this O tilde notation. So the O of h of n times these logarithm factors of n is exactly the same as the O tilde of h of n. So the O tilde ignores logarithm factors. And I have 2 examples for you, or 1 example and then 2 exercises. We can say n log n times the log of n is O tilde of n. And I have 2 more examples for you, and I quickly want you to look at them and think about what their O tilde could be. So the first term here is n squared times log n times the log of n. What O tilde is that? It's O tilde of, if you have a guess, send it to the chat. It's O tilde of n squared, because we make all these logarithm factors disappear. And the next one is also n times log n squared times the log of n. It's just O tilde of n. So if you read some papers about quantum computing sometime in the near future, maybe, and you see this O tilde notation, you see what it's useful for. There is one more thing that is maybe something that isn't too important to you when you study complexity theory in your first round, but it's something that is called pseudo-polynomial complexity. I will briefly explain what this whole thing is about, and maybe in a few weeks' time, when you feel more comfortable with complexity theory, maybe go back and just read this article on Stack Overflow. The pseudo-polynomial complexity is nothing that is the focus of this course, but it's maybe just some expert knowledge for further understanding. Someone describes in this Stack Overflow article an algorithm and says you put in an integer n as the parameter, and you actually want to do integer factorization. So you put in an integer, and what are its factors? For example, you put in 10, its factors could be 5 and 2. And what this person noticed is if you put in integer of n and you do a complexity analysis of this algorithm, it actually starts to look like that this algorithm has a linear complexity, which confuses the poster because factorization algorithms are extremely hard and they take usually something around exponential time. and this person wonders, hey, I put down an algorithm here and I put in an integer n, and somehow it should be exponential, but when I do a complexity analysis, it's O of n. And it turns out something went wrong, because when you put in an integer as a parameter, our complexity theory doesn't really work the way we have used it so far, because we have always put in some input data structure. For example, a sequence of n elements. And then our complexity theory approach worked. But when you don't put in a data structure, but rather just an integer, then you need to approach your complexity theory analysis differently. If you approach it the way we have done it, you will end up with pseudo-polynomial complexity, because this one here, it looks like it's polynomial complexity because n is a polynomial, so O of n. But in fact, this algorithm is not polynomial complexity, it's exponential. And what appeared here is the poster did not put in a data structure, but only an integer value. And then what he or she created was a pseudo-polynomial complexity. This is something that is more like expert knowledge, but if you're curious about this issue of pseudo-polynomial complexity, take a look at that Stack Overflow article and maybe give a read and see what it's about, because there is a proper explanation of this concept of pseudo-polynomiality. But if you're new to complexity theory, maybe that's more something to go back in a couple of weeks to. It's also nothing of the focus of this course, because in this course, for the algorithms that we use, we put in some data structure usually and not just an integer. We may do this rarely, but when we do this, we will not run into the issue of pseudo-polynomial complexity. So more like an expert chapter, but maybe something you wish to read. Now, one last note on complexity theory. What we have done so far is time complexity. We have wondered of how much computing time does an algorithm need in terms of primitive operations. You can apply the same concept to space complexity. And space here means how much RAM does your algorithm need. There are some algorithms, they may run very fast, but you need to build a huge cache in your memory. So they may be fast, but they need a lot of space, while other algorithms that do the same task, they need a lot of time for computing, but they don't use a big cache, or maybe just a very little cache. So typically you have to make a trade-off between time complexity and space complexity, because our framework of O, theta, omega, and so forth also needs to be applied to the issue of space. You can apply it to time as well as to space. And if we just go back, for example, to our prefix averages, we saw that this algorithm here takes O of n much time. Anyone has a clue or view of how much space this algorithm needs? It's O of what? If you have a suggestion, just send it to the chat. And maybe look at what we are creating, and we got the right answer. This algorithm needs O of n much space because we are creating this new output and we will return it. And it has the length of n, so this algorithm also needs O of n much space. There are some other constant factors like n or the total, but their size, they're just primitive data types. Their size does not depend on n. So these are constant ones, but you spend your extra memory on this A. In this algorithm, this is simply by nature because we want to return a new list. But with other algorithms, you may need to make a compromise between time and space. And our whole framework of O, omega, theta can also be applied to space and not just time. We have finished now the introduction to complexity analysis, and we need complexity analysis throughout this whole course because we'll now be looking at lists, which are a fundamental data structure. We'll be looking at sorting, we'll be looking at trees, so more algorithms and data structures, and we always want to assess how efficient are our algorithms, how efficient are our data structures, because we want to build them efficiently. And the issue of space complexity will be of particular interest when we look at recursion. So when a function calls itself, this creates some extra memory usage for technical reasons in the operating system. And when we get to recursion, we will refine our knowledge of complexity analysis. We will look at space complexity, but we will also look at time complexity of recursive algorithms, because recursive algorithms, they work quite different to our algorithms we have seen so far that are iterative and use loops. And assessing the running time complexity of recursive algorithms is not that easy. And we'll see some tools of how to do this. But this is something we'll be doing in a few weeks' time because we're now starting with lists. We have used lists so far in Python. Those lists are natively embedded in the language. And we actually want to see of how to build such lists. Lists are based on arrays, and arrays are static, and so-called dynamic arrays are also referred to as lists. We'll be looking at them. And a list is a dynamic data structure because it keeps growing when I add more elements. And this also has impact on my complexity theory. And we will briefly look at a concept that is called amortization to better assess the time complexity of dynamic data structures. And then we'll be looking at some variations of lists. For example, we'll look at linked lists at the end, but we will also be looking at queues and stacks, which are just variations of a list. And there are different data structures with a different purpose. And we will try to implement all of these data structures efficiently so that you can easily, or that you can build them in an efficient way. We will now look at low-level arrays in Python. And in order to make it there, we first of all need to revise what kind of so-called sequence classes we have already seen in this course. We have seen lists, and a list is a so-called sequence in Python. A tuple is like a list, but it's immutable. And a string, we have also built various strings. Strings are also sequences. You can also imagine a string as a simplified way as actually a list of characters, if you look at it from a very primitive view. And the one thing you can do with these sequence classes is you can always index them with an index k, and you can randomly access in there, or you can use your random access memory. And internally, these sequence classes, they use a lower-level concept that we call an array. And internally, they use this, but they hide the details of the array, and they provide you with a high-level public interface. If you have done Java or C++, you have definitely created arrays. It's something you don't see too much in Python, because in Python, this is quite a low-level concept that we rarely use, but today we see how we can actually create so-called arrays in Python. An array is an area in your RAM, and your RAM is your random access memory, and your RAM in a modern computer is something like 8, 16, 24, 32, 64 gigabytes, whatever. And internally, your RAM is organized into bytes. And the bytes are 8 bits. And each byte in your RAM has a memory address. And one thing that is very, very helpful about your RAM in your computer is you can efficiently access every memory address in constant time. So, or near constant time, but for us, it's just O of 1. So it doesn't make a difference in terms of the running time, whether you access this byte or this byte, because you don't need to linearly go through those bytes. Rather, if you have the memory address, you can directly access that part in your RAM in constant time, both for storing as well as reading, which is something super helpful that you cannot do, for example, on a hard disk, on a classic hard disk, or on a tape, because there you need to move something physically. And with a RAM, you can do this efficient access for storing and reading. And we'll now come to the concept of an array. Somehow we need to organize our RAM, and we may want a certain piece in our RAM and use this as a so-called array. And an array is a contiguous portion of your RAM. And in an array, you can store different things. For example, you could store integers, but we can also represent a string as an array. Now, for example, on many computer platforms, characters are not represented in ASCII format anymore, but rather in Unicode format. And with Unicode format, what we can do is and with the Unicode, we can represent more than just ASCII. And the Unicode character usually has 16 bits, meaning 2 bytes. And then you can create an array of a certain length, which is a fixed length, concretely 6 elements. And what you need is, because in each element you're storing 2 bytes, you need 12 bytes in order to represent these 6 characters. When you create that space in your RAM, or when you create that array, some things are important. Arrays are contiguous. Once they are created, you cannot just extend it, because maybe the operating system later puts something else in here. So you cannot just index outside the array. And within the array, you have an abstraction, because the elements in your array, they have an index. So you can say the first element is index 0, the next element is index 1, but you don't care about how big each element is. If an element is 1 byte or 2 bytes, you don't care, because all you need is your index in order to access the right element within the array. You can also refer to an element in the array as a so-called cell, if you wish, and they have indexes. And as I said, when you create an array, it's a fixed size, and you cannot just extend the array later on, because maybe for the next element, there's already something else stored in here. So you cannot just extend your array. So it's fixed size. But we will have another challenge. Later, we will see of how we can grow arrays, or how we would emulate this. But something that can also happen is, if I have my array here, what I've stored in here is I have all these characters, and each character is 2 bytes. But I could imagine a different scenario where I want an array of strings, for example. So this time, before, what we had was an array which stored 1 string, and now I want an array that stores multiple strings. And these strings, they may have a varying length. These are names. One is Renee, the other one is Joseph. We have longer names like Virginia. And if I try to store this in some kind of array of strings, and I assume a string is an element in my array, I will run into lots of problems, because we've seen that each element in an array must have the same length. So I would sort of be required to take the longest string possible and say that each element in that array has exactly that length, or maximum length. So I would be probably wasting lots of space if I have a super long name, and this would be the size of an element in an array. And then I have lots of shorter names. So that would lead to a lot of waste of memory. What I'm doing, in fact, is I'm using a referential array for such problems. And I have an array where I'm not storing the exact strings in an array position. Rather, I'm storing these strings somewhere in memory. They're not connected. I'm just storing them somewhere independently of each other in the RAM. And each string has a memory address where it starts. So I could think about that each of these strings is an array itself that I'm storing, but these arrays have different lengths. And I'm storing the memory address of the array, meaning the first element in the array, in my actual array where I want to store all the strings. So the array of strings will not store the strings, it will only store memory addresses. And in those memory addresses, I'm storing the individual elements. This is a super important concept that I use referential arrays. And when I try to copy such data structures, I need to pay attention to something. And this is something I will quickly explain on the iPad. So we'll have our referential array. And my array has elements 0, 1, 2, 3, and 4. And they store some objects that are somewhere in memory. And what these objects look like exactly doesn't matter, but we can still name them. This would be object 1, object 2, object 3, object 4, object 5. Could be strings, could be something else. And this is my array that I call A. And now I want to copy my array and create an array B. And what I can do is I can just copy array A into B. So for each index, I'm just copying the memory address. Because there was a memory address in here, I put it in there. So this, again, the index is 1, 2, 3, 4. And eventually, I'm copying the memory addresses that I stored in A into B, but these memory addresses are the same. So I'm still referring to the original objects. And what happens now, if I go, say, to element index 2 in array B, and I change the object to which I'm referring, so I'm going to the object and I'm somehow changing the object, then array A will also be affected because array A has also referred from position 2 to that object. So that object is shared between the two arrays. And the copy I have done is a so-called shallow copy. A shallow copy means I'm just copying that array and I'm copying the memory addresses to the objects, but I'm not copying the objects itself. That's a shallow copy. We call this B1. And B2 would be a different kind of copy now. In B2, I am first of all copying the objects. So object 1, object 2, object 3, object 4, object 5. And these objects that I have copied, so these are copies of object 1, 2, 3, 4, and 5. I have copied them, and in my new array, B2, I am referring to the copies. And then if I change, for example, the object to which index 3 references to, I change this object 4. I'm just changing this one, but not the original object A4 to which array A has referred to. And this kind of copy is a deep copy. So I'm not just copying the memory addresses, but I'm copying the objects itself. This is something you will see quite often when you try to copy data structures. You need to ask yourself if you want to do a shallow copy or a deep copy. When you do a shallow copy, you just copy memory addresses, but not the objects. And then when you manipulate the objects to which the original array referred to are also manipulated because it's the same objects, but a deep copy would also copy you all these objects. So if you change them, the originals are not affected. This concept of shallow copies and deep copies is also explained in the book, for example, in chapter 521, where if you're curious about the concept of shallow copies and deep copies, give a read in it. But I've just discussed the essence of what's the difference between a shallow copy and a deep copy. And maybe you can give me a signal. A green sticker is you got the difference between shallow and deep copies, or maybe a red sticker if you still struggle with those differences. There's a large majority for understood. If you struggle with these differences, maybe just look at the recording of what we have recorded just now, or take a look at the book where you may get some more examples of the difference of shallow copies and deep copies. Now we will actually build so-called dynamic arrays. We have seen that this is an array and it has a certain size. It has 6 elements. In total, it's 12 bytes. But I can change an individual element. That's totally fine. I could change this M to a Z or whatever, or the L to an O. But I'm not able to change the size of the array. So there can be 2 problems. Maybe I want to add more elements to the array. That's not possible. Or maybe I create an array up front as a storage, but it's way too big and I'm actually not using it to that extent. And I'm wasting a lot of space in the RAM. So these are issues that may arise. So we want an actually dynamic approach, and we want so-called dynamic arrays that allow us to grow or shrink over time. And these are called often lists. And the lists in Python that are natively there, those are dynamic arrays. And we will now see how they work internally and how to build our own class to do lists. I will show you this directly from this figure. So this is here just the step-by-step procedure, but the next slide is a figure to show this directly. Imagine I have an array A and it has 4 entries and it's full. And now I want an array that is bigger. I want it to have more space, but I cannot just grow the array A. Rather, I have to create a new array in the RAM, and I call it B. And one approach that is convenient is that it's just a double size. So when you grow, you don't just add one element, because this leads to lots of, when you want to grow, you cannot grow, so you have to create a new array. And you want that one to be sufficiently large, so you don't need to grow all the time. Then I have my array B, which has the double size. It's empty. And what I'm doing then is I'm copying the addresses that are stored in A to these objects into B, into the first 4 spots. Now, both A and B refer to these objects. And then I can delete A, and my new array that I had put here, I assign it now to variable A. So now I have a variable A and it refers to a new array in a different piece of the memory that is a copy of the old array and the addresses to the objects. I don't touch the objects, I only copy the addresses to the objects. Plus I have more space in my dynamic array in order to add more elements. This is how you grow an array. So you're creating a new array, and the new array will be referred to with the variable name from before. This is also explained here in a step-by-step procedure, but I think an image is much more helpful. And we will now try to code something like this step by step. So we are building our own string class, our own list class that works a little bit like the one that you natively get in Python. And once we have built it, we'll be thinking about its complexity. First of all, I need some strange import that we see later. ctypes is actually a module in Python that allows us to do these low-level operations or deal with low-level arrays. But we will see this at the very end. We don't need this for now. Then I'm creating my new data structure and I use an object-oriented approach. So I call this my array. And my array needs an initializer with no parameters, but I always need to put the self parameter explicitly there in Python. We've seen this. And I want to have various parameters. For example, or not parameters, attributes in my class or for the object. I want an attribute n where I say this is how many elements I'm storing in my data structure right now. Initially, it's 0. And because in Python, there is no distinction between public and private attributes, because you cannot pass this as a keyword, a convention in Python is, since everything is public, you indicate the attributes that you consider private, and you indicate them with an initial underscore. It's just a convention, it's still public, but like this you indicate, don't touch this, it's considered to be private. We also want our data structure to have an initial capacity, a certain number of elements we want in there. And we say for our dynamic array, our list will just have one element for now. And I also need a storage where I'm actually keeping a reference to the actual low-level array, because we're building a dynamic array, a list, and somewhere I need to store this low-level array. And we will have a helper method that we call makeArray. It's also considered to be private. This one allows us to create internally an array, and I'm passing a capacity for which I want to create this. Later, we will see how we build this low-level array. It doesn't matter for now. Then we will, later I want something that if I have my object of my array, I want to be able to call the len function, which is natively in Python. And with len, we could apply this to a list to get its length. And we also want our list or our dynamic array to be accessible like this with the native length function. So I need to implement an internal function, and this is Python specific. You would only see this in Python. In other languages, it looks different, where you have an len method, and it starts with 2 underscores and ends with 2 underscores. And if you call the len function of an object, then the class's method len starting and ending with 2 underscores will be called. This is a convention in Python, and what I'm returning is just my n attribute, because this is how many I'm storing right now. The capacity is how much I can store at the most, but how many elements I'm storing right now, this is done with the n. What I also want is, if I have later my object, I want an index, like some index I, in order to read it out at index I. And for this, again, in Python, there is a special function which is called, or a special method, getItem. And getItem has a signature that looks like this. GetItem, again, starts and ends with 2 underscores. You have your self reference, which you always need to declare explicitly. Plus, you have an index k, and this k is that index you're passing in that index. that value, and we could now return self at index k. Because we can say self A is our low-level array. We'll later see how to create it. And I can index an array because it's stored in a RAM with k, and I'm returning this. Do you think this looks fine? Maybe without looking at the slides, because I want to develop this step by step with you. What could be some problems with that index? If you have any guess, you can also turn on your microphone and talk to us or send this in the chat. What could go wrong with this index? If you have a clue what could go wrong, maybe send me a thumbs up or something. So I'll wait for you in the chat and I'll see if anyone has a suggestion or if I shouldn't wait. And there's a thumbs up. So maybe you want to share this in the chat or turn on your microphone and share your insights with us. What could be going wrong here? So we should check if k is actually valid. So we should check if k is actually less than our array length. So we could check if k is less than the length, because indexes are 0, 1, 2, 3, so it needs to be a less sign and not an equal to sign. And then I can do this. But what if k is negative? It could be negative, and I don't want negative indexes. And in Python, I can write such constraints in a very nice way. I can write if the following condition is not satisfied. So if not the following, k is less than self n and k is greater than or equal to 0. With these double inequalities, this is something you cannot do in a lot of languages. In Python, you can do it. And if this condition does not hold true, then we have a problem. And what we're doing is we are raising an index error. An index error is an exception class that is natively available in Python. And I raise an index error and I say it's an invalid index. If this if is true, so if not something is true, I raise this. However, if I don't raise the exception, then I'm fine. Then it's a valid index and I can return it. And it's important I compare this to self n and not the capacity, because I only want to be able to access valid elements that are stored, and I don't want to be able to access placeholders where I haven't stored anything yet. Then I also want to append. I want to be able to append an object at the end. So what I can do is I can say I'm appending an element like this. I say I'm increasing n, and self A is our array. I need some index and I want to store the object there. And for the index, I use the largest index or the next index that is free. And we know self.n stores how many elements I have in, and index n is not available yet because indexes are 0, 1, 2, 3, 4, and so forth. And n is just the next free index where I'm storing now the next element. So I'm saying self._n is the index for variable a, and this is where I'm storing the object. What do you think can go wrong when I append this? If you have an idea what could go wrong when I'm trying to append, let me know. Again, if I shall wait for you, thumbs up, but we got a good comment. We can run out of space. So maybe the underlying array is full, and this is our scenario we saw before, what we had seen in the figure. So I need to check if I'm actually running out of space. And I'm running out of space if my current index, if my current number of elements n is the same as the capacity. So if I have a capacity of n, say a capacity of 10 elements, and my n is, I have 10 elements in there, I'm full. And if that's true, I need to resize, and resize is a new helper method. And my helper method, resize, I will pass the double capacity. So we've seen this as a convention before. I'm just doubling the capacity, and this is my new capacity. Now I will think about how can I resize. Resizing, I pass my new capacity. And I know if you learn coding and proper software quality, you use like very expressive names, not just A, but this is an algorithms course where I just want to keep the variables short. And that's why I use an A or a C for the capacity. And we got a question here in the chat. When do I use underscores and when not? I use underscores for attributes. So what I'm storing in the object context, if it's private. So private attributes, I would give an underscore. Local variables or parameters, they don't use leading underscores, only for private attributes. So what I'm creating in the constructor and in the method declaration, I'm using also an underscore for methods that are private. So what's public is obviously appending. Public is also length and get item and the initializer, but they start and end with 2 underscores because this is how it's internally realized in Python. So I have no control over this. And when I'm defining new methods, append is public because I want this to be public. Obviously, the constructor length and get is also public. And resizing is something I don't want to be able to call from outside because I just want to deal with a list. I don't care about how much free space it has. Simply, when it runs out of space, it should resize. So resize is also private. And now I'm just doing what we visualized before. I'm making a new array. We will later implement how to make an array. This is our last piece we are building. Then I will do a loop, and I'm actually going through all the elements in my array. And this is now a low-level array. So I need to look at the range. I need to look at the range of n. So how many elements I have in there. And I go through the index. So this starts with index 0, index 1, index 2. And then I'm copying from A into B. Remember, B is a local variable. Underscore A has object context, so it's an attribute. And then I'm copying all the elements from A into B step by step. Now I'm done. And actually, I want A, so underscore A, to refer to my new array because I've just created the new array. I don't need the old one anymore. And so I can say self._a refers to my new array that I have created here in the RAM. And I'm also updating my capacity. And my capacity is the new capacity. If you have a background in C or C++ and you implement it like this, you will fill your RAM with arrays that you cannot access anymore because A referred before to some old array, and I'm just changing the reference in A to the new array. If you implement this in C or C++, you need to manually free beforehand the memory where A refers to before you override the address in A. In Python or Java, you don't need to do this because there's a garbage collection So I'm just writing this here behind. Garbage collection takes care of old A, so it will delete this old array, and you don't need to handle this on your own. There's one last piece we need to build. It's our make array. And make array, all it does is it creates a low-level array in Python. And for this, we need our C types package. And what this does is the following. C types was imported, and I'm creating a Python object, concretely capacity C many ones, and I'm calling this as a function. How this works exactly here is something we don't need in the remainder of the course, because this is probably the only time we are creating such low-level objects. So this line here is just something we use. If you're curious about how the C types works internally, look it up, but you don't need this for the remainder of the course. It's just a low-level helper to build low-level arrays. So this one is probably the least relevant line in this code. And now we can build it. We can build objects. So I can say this is my data, and it's an object of the myArray class. The length of data is 0. We can, if we want, peek into the private elements. This is forbidden. We shouldn't do it, but we can do it because it's not private. We see the capacity is initially 1, and we can now append something. We can say append a 100. Now we can see the length of data is 1. The capacity is still 1. And if I want to append something else like a 200, the length of data is 2, and the capacity of data is also 2, because we said we will always double the capacity. Now, if I append a 300, we will see the length of the data is 3, and the capacity is 4, because we always double the capacity when we run out of space. This is also something you can investigate very well if you run this in the debugger, for example. And like this, you can use the debugger to look into your object and see how it works. We can also try to use the index now. We can say what's in data at element 0, that's a 100. At index 1, it's a 200. And at index 3, it's not valid because index 3 does not exist. But index 2 is a 300. And an index, say, -1, is also not allowed because we don't allow negative indexes here. So we have easily built our own very simple list class for now. It's not as powerful yet as the one in Python, but we will step by step try to build our more complex data structures. What I have coded for you is also available in the slides, but I think the live coding session helps to discuss every line of code. And you can also find this code implemented in my Nextcloud directory. There's a zip file with various code examples in. So this is what we have done. We've also discussed the C types module. Now we can be more thinking a little bit about complexity of all of this. The complexity looks the following. Accessing the length of our data is just constant, because all we did in there was we stored the length, and we read it out, and we say, well, we just read out n, which is the length, and just reading it out is 0. Accessing for reading at an index is also just constant, because all I'm doing is I'm looking at the array's position. If you look at the Python list class, there are much more operations that the Python list class offers, like to count something, trying to find the index of some value, and many other things. These are the functions we have not implemented, but you will see the complexity here of the implementation in the native list class in Python. Now we run into, and the space complexity is O of n because we have n many elements in the list. And we can run into some strange problem now that I want to discuss with you. And maybe I go back to our code for this in order to show you what the problem is for appending. What do you think is the complexity of append? It's O of what? And I want you to have a guess by looking at our implementation and send to the chat, what do you think is the operation, or what's the O of appending? I'll give you a moment to think about this. If you have a guess what the O complexity of append could be, send me maybe a thumbs up or a thumbs down if you have no clue what's the O complexity of that method. And if you have a thumbs up, one student says either O of 1 or O of n. And this becomes quite interesting because if this condition does not hold true, I'm skipping the resize and I'm just writing in an index and increasing n. So for the best case, I'm actually just using an index here. I'm assigning a value. I'm increasing n. All of these are primitive operations. So it's constant time for this one here. But in the worst case, n and capacity are the same. So I need to resize, and resizing is O of n because I need to create a new array, and I need to copy all elements. So this is O of n in resize. And sometimes in appending, I need to resize and sometimes not. And I told you in our framework, we always assume the worst case input. So the worst case is really that I first need to resize before I can store. And we always assume the worst case in our O framework. That means appending is O of n. But maybe that expensive part doesn't happen too often. And what I have just said is also written in the slides, but I'm skipping that for now. And it's just for your revision. But we can also see that actually the resizing doesn't happen too often. Initially, if I store one element, I can just store one element. If I want to store element number 2, I can store it, but first of all, I need to copy that first element into my new array, which has size 2 or capacity 2, and then store my element. And so forth. So what we see is, from time to time, I need to resize. If I have stored, if I'm storing the third element and I have enough space, I can just store it. But from time to time, I need to resize. And I'm always resizing when I'm storing one more element and I don't have enough space. So I need to copy all the past elements. And then that takes n much time because I have n much elements. And then I'm storing the additional element in it. And the larger my data structure gets, the less often I actually need to resize, because if I have the size 1024, I can add then the 1025th element, and then I can add, when I have size 1024 and I double it to 2048, I'm storing the 1025th element, and then for more than 1,000 times, I don't need to resize. I can just store another element in it. So resizing happens less and less often as the data structure grows. But we always say that appending is O of n, but this worst case actually doesn't appear that often. And this problem can be addressed with a technique that we call amortization. With amortization, we can assess operations like append in a slightly different and probably more accurate way. Because if I need to resize, this actually doesn't take O of n. We can more concretely say it's theta of n much time, because resizing, I really need to copy all n elements. So the upper and lower boundary is the same. But then when I have resized and stored that element, I need to wait potentially many more times until I need to resize again, because I've created more empty space. And then just adding these new elements into the empty space I have there just takes O of 1. And this can be expressed with a term like this, where I say, if I have n plus 1 many insertions or I append n plus 1 many times. One of those times, I have the theta of n time where I need to resize, but n many times, I don't need to resize and I can just store in the free space. And that storing is O of 1 or theta of 1. It's even a better statement because storing is really just constant because I have these few primitive operations and I store n many times, and one more time I need to resize among these n plus 1 many attempts to append. And if I look at this term, this will actually lead to constant time in average. Not in the worst case, but in average, because in average, it's just super unlikely I need to resize, and among these n plus 1 many times to append, only once I actually need to resize, and the n other times I don't. So I can introduce a concept that I call amortization, and amortization is sort of like an averaging, more or less, of how much of the complexity, taking the growing of the data structure into account. So what we saw before is our appending is actually O of n, because the worst case may happen. But that worst case is unlikely. So with amortization, we can say, well, appending is O of 1 if it's an amortized running time, taking this into account what I just explained. So when you write amortized complexities, you would write O of 1, and then you would have put a star, and somewhere you would explain what the star means. And the star is amortized. If you just write O of 1, it's wrong, because the worst case is O of n. But with an amortized complexity, you would write O of 1 and then either write in parentheses amortized behind or put a star and explain what a star means. But somehow you need to emphasize that it's an amortized complexity and not a worst case complexity. And for the Python list that is available natively, there are much more methods which come with certain complexities. We're not discussing them here in detail, step by step. Some of those methods we will see again in this course. There are also some in the coursework for you to implement, but always make sure you distinguish between complexities, which are worst case, and amortized complexities. That's what we have done for today. Next week, we will look at a different data structure, which is called a stack, and I'll explain it next week to you. If you look into the coursework, because I'll see you again next week, Friday in the morning, we will also have time to look together into the coursework. You can do all the coursework from the complexity analysis chapter, so up to 8.3, and you can already get started with exercise with problem 9.1 and problem 9.2, because here we have our myArray class, and you have to implement a few new methods like setItem. So you can use an index for setting an existing index. Insert does something slightly different. You would insert a value at a certain index and move the remaining ones to the right, or remove a certain index. If you want to know how or what these methods setItem, insert, and remove are supposed to do, maybe give a try at the native Python list first, and look at its documentation, and there it's explained what these three do. And then there's also problem 9.3, which you have this getItem, which we just implemented, but it should also be able to handle negative indexes. And we saw this in the intro to Python, that, for example, negative index -1 is just the rightmost element. -2 is the next one to the left, and so forth. So maybe you can amend your getItem so it can also handle negative indexes, but you need to make sure it's a valid negative index and it is not too large. This is the coursework you can do next week on Monday or until then, and I'll be happy to discuss any questions you have on the coursework. And next week, we'll continue with stacks and queues, which are other data structures built from lists. And we'll also look into linked lists next week. If there are any questions, maybe send me some signal now. Otherwise, we are done. And with there not being any reactions, I guess you're okay. I wish you a good weekend and see you next week in the lab. And also, please go to the tutorial on Tuesdays, because the teaching assistant, I think he does a terrific tutorial, and he's also there to help you in case of any questions. Have a good weekend. Bye-bye.